What is cosmology? Cosmology is the attempt to answer some of the greatest questions that have ever posed to humanity. How did the universe begin? What is the universe? Why are we here? What makes up the universe? When will it all end? What's it made out of? What's the eventual fate of the universe? Is there a meaning? And most importantly of all of that, how can we learn anything about any of these questions? Cosmology seeks to answer these questions using experimental science and measurement to understand the origin and fate of the universe. We attempt to make models of the universe in various ways and see which ones work, which ones fit observations, and then make observations that either to test those ideas. And if the ideas don't fit the observations, then we have to discard the ideas. And if the observations are challenging and new, then we have to understand them with new ideas. The universe itself is very vast. It is composed of things like people and oceans and planets and stars and galaxies. And it is composed of normal matter, dark energy, and we think of the things that go from the very smallest to the very largest. And we look at the cosmic microwave background, we look at the origin of things from the Big Bang nucleosynthesis. We look at our place in the universe, where how it has changed from being thought from ancient times when we thought we were at the center to now we know we are one of a multitude of galaxies in a vast cosmos. With that very brief introduction to the concept of cosmology, I'd like to welcome you. My name is Jason Kendall. I have taught cosmology at William Paterson University. I have also done quite a bit of things, as you probably have seen on my YouTube channel, for introductory astronomy. And so I figured I'd put my cosmology course on my YouTube channel. If you wish to follow along, you can certainly do so. I am utilizing as my basis Dr. Barbara Ryden's textbook, Introduction to Cosmology. She's a professor at Ohio State University, and I've used her textbook in my course at William Paterson University in the past. So why am I doing this? Principally because cosmology is really enjoyable to me. It's what I have my master's degree in, and I find it a fascinating subject. So what should you expect? We're going to go through this textbook, and I'm going to hit every single chapter and every single section in it. I'm going to derive mathematical equations and give you the theoretical and observational understanding for what cosmology is and where and what we can understand from it. In order to understand anything about the cosmos, we have to understand how to measure it. Because in any science, no matter what it is, you have to be able to measure things. You have to have reliable ways of measuring those things, and you have to agree on what you're going to measure on. So part of the agreement of understanding measurement is the units that we use to measure things by. And the standard thing that we're going to talk about, some basic units to begin with as this introduction. We will introduce to the idea of distance. We know about meters. Meters are about 1 meter long. Most of the world knows what a meter is, but in the United States, we like to think of yards and not meters. But we're going to stick with meters. And the meter is a standard sort of human-sized distance, and the kilometer is a standard human-sized distance. But the real astronomical distances start when we look at the astronomical unit, or the average distance between the Earth and the Sun. That is 1.5 times 10 to the 8th kilometers, or 150 million kilometers. The next most interesting thing from the astronomical unit for a unit of distance is the light year. And that's mostly a kind of a cultural thing. It is the distance that light will travel in a year, which is about 10 to the 13th kilometers. More important than the light year is the parsec. The parsec is a geometrically derived observational distance to something that's very far away. A parsec stands for a parallax of 1 arc second. So what's that mean? Parallax is that apparent shift that you see in something when you say, hold your thumb. Let's say that something is your thumb, and you hold it at arm's length, and you blink your eyes left and right, and your thumb appears to shift in position with respect to background things. Now, that shift might be big, might be a degree or so, and the distance between your two observation points, your eyes, is only a few inches. Let's say now the observation points are now separated by 1 astronomical unit, and the angular shift of your thumb is now 1 arc second and not a degree or 2 or 5, or not even a half a degree, not even a tenth of a degree, but 1/3600th of a degree. And that means that it's going to be very far away because that shift will be very small and the baseline is very large. So you're going to have to be really far away such that a really large baseline, 1 astronomical unit, will give you a very small shift. And that ends up being about 3¼ light years, or 206,264 astronomical units. That's the distance. But this is a geometric distance, and so there it's a direct observational. And therefore, it's really important and better than light year because uh, photons don't have clocks attached to them, so a light year is really kind of meaningless. So this is the main geometric measurable distance to the stars. And the typical distance between stars is about a parsec or so. But when we think of the largest collections of stars, like the Milky Way or galaxies, we have to start measuring the distances to galaxies in terms of megaparsecs, 10 to the 6 parsecs. And then when we think of distances or size scales of galaxy clusters or distances between clusters, we start thinking in terms of gigaparsecs or billions of parsecs. For some basic ideas, the distance to the nearest star is about 1⅓ parsecs. The distance to M31, the Andromeda galaxy, is about 3/4 of a megaparsec. And the Virgo cluster of galaxies is about 16 or 17 megaparsecs. The size of the observable universe, the size from if we look one direction and turn our heads 180 degrees and look the other direction, that is the observable universe. And that goes in any direction with which we look one way than the other. And the diameter of that is approximately 28 or 29 gigaparsecs. So these units of distance are very large. The next unit we'll talk about is the amount of stuff there is in a place, and that stuff we will call mass. And mass has a very interesting set of properties. But we will first say that we'll kind of agree that we understand what mass is and that it is some accumulation of stuff. And the standard unit in the SI units is the kilogram. And kilograms are pretty important, but for astronomical and cosmological purposes, they are not. More importantly, we use the solar mass, or the mass of the sun, which is about 2 times 10 to the 30th kilograms, which is a lot. And the mass of our Milky Way galaxy is about 1 trillion solar masses. And the mass of the Virgo cluster of galaxies is approximately 10 to the 15th solar masses. The solar mass is a very good unit, but we can see that galaxy masses can be somewhere between a billion, or very tiny galaxies on 1 million or so solar masses, up to trillions of solar masses for the very largest of them. So our unit is going to be the solar mass for our base unit of measurement. Just as important as mass and distance is time. Time is really important for physics because it doesn't matter if there's a thing over there that has mass and it's over there at that distance. We want to know how things work. And so things work means that there must be some time that's involved. And in the units of time that we know are, of course, seconds, which are like the second minute of an hour, which is a very interesting way of thinking about it historically. And finally, we will continue with the idea of the second as in the Earth year, the time it takes the Earth to go around the sun, which is about 31.5 million seconds, or pi times 10 to the 10 to the 7th seconds, which is really close to pi times 10 to the 7th seconds, which is fascinating. Anyway, but cosmologically, that's not very important. The second, even the year isn't important. Cosmologically, we more think of things in millions of years, like mega years, 10 to the 6th years, or giga years, 10 to the 9th years. The age of the Earth is about 4.567 giga years. The age of the Milky Way is approximately 13.5 giga years. And a characteristic age for the universe, which we call the Hubble time, is about 14.7 gigayears. And these are the types of time units that we care about cosmologically. We really do care about millions of years and billions of years in cosmology. Now, once you take some stuff that has mass and it's over there and it is moved from there to here, it takes energy and work to move things from here to there. And so we have to then define also the units of energy and power. The standard SI unit is the joule, and or we can also call it a Newton meter. And the units on the units of energy are different because they're made up of mass and distance and time. The unit of energy is a kilogram times a meter squared over a second squared, or a Newton meter, which is a unit of force, which is a kilogram meter per second squared, exerted through a meter. That is the unit of the Newton meter, or joules in terms of the base units of mass, time, and distance. So the watt is 1 joule per second, which is another SI unit. And next we have the good astronomical unit of the solar luminosity, or how much energy the sun is putting out every second. That's about 4 times 10 to the 26th watts, which radically dwarfs the entire output of humanity, which is on the order of some numbers of hundreds or thousands of terawatts, which is only 10 to the 12th. So the sun puts out a lot more energy than humanity ever will. The luminosity of the Milky Way can then be measured in solar luminosities at about 3 times 10 to the 10th solar luminosities. And you can have extraordinarily bright objects that can be seen from extreme distances like quasars. And specifically, an example quasar is 3C273, which has about 4 times 10 to the 12th solar luminosities. And all of that energy is being created by a supermassive black hole at the center of a distant, distant galaxy. And we will be using energy and power often in the quest of cosmology and astronomy. In addition to these extraordinarily large units of distance, time, and energy and mass, we also are concerned with the very small, because the universe, as we will find, was started in a very hot, very dense, very small place. Well, not really place, but state, rather. And so we have to understand the units for the very small. And the joule is sometimes too clunky for that. And we would rather use a unit from, say, particle physics, because we're going to be talking a lot about particles and how individual electrons and protons, or huge masses of them, contribute to the cosmos. So a useful unit on particle physics size scales is the electron volt, which is the amount of energy that an electron gets when it is accelerated through a potential of 1 volt. And it's a very, very, very tiny, tiny energy. It's 10 to the minus 19th joules. It's a tiny energy. The electron volt's a very useful thing. It's used in particle physics, and you'll use it in laboratory experiments and in undergraduate physics labs too. Importantly, we just remember that the rest energy, which is the E equals mc squared from Einstein, the rest energy for an electron is about half of a mega electron volt. And the rest of the proton rest energy, meaning how much energy it has simply by existing, that's what rest energy is just under 1,000 mega electron volts, or almost a giga electron volt. Now, a neutron is almost the same thing as a proton, but just a little bit bigger. The neutron's rest energy is a touch bigger because it is neutral. And so in order to make a neutron, an electron and proton have to be combined in the presence of a neutrino. But the energies, the rest energies of these particles, is on the order of a giga electron volt, or 1,000 mega electron volts. Now, the size of a hydrogen atom is very small, so those are their energies, but their rest energies, the energy for existing. The size of a hydrogen atom is about an angstrom, which is about 10 to the minus 10th meters. So we talked about meters, we talked about light years and parsecs and gigaparsecs, but we also care about the size of a hydrogen atom, which is 10 to the minus 10th meters, and the size of a proton, which is extraordinarily small at about 2 femtometers, which is 10 to the minus 15th meters. So that's a 0 with 15 with a dot, then 15 zeros, and then a 2 after that. That's the size of a proton. And so you'd have to stack 10 to the 15th protons up in a row just to get 1 meter. Or if you think about it, to get 10 to the 13th in order to get 1 centimeter. So that tells you roughly how many protons there could be across your thumb if they were stacked that densely. They aren't stacked that densely, but in some astrophysical cases they are. But the very small are also incredibly important for cosmology because these small environments arise when we talk about Big Bang nucleosynthesis. Just as important as these base units are what exactly we're measuring. And we have found over the course of hundreds of years of exploration and discovery and scientific advancements that there are some fundamental constants in the cosmos that stay put. The speed of light in a vacuum, which is 300,000 meters per second, or 300 million meters per second, or 300,000 kilometers per second. Newton's gravitational constant has that value of 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. And that's an interesting thing because the equivalent units are like meters cubed per second squared per kilogram. It's interesting that you have a meters per second as a fundamental constant and something that has meters on the top and seconds on the bottom and kilograms on the bottom as the equivalent units. Newton's gravitational constant obviously is the thing that relates the force of gravity, force due to gravity, as discovered and elucidated by Newton when he said the force between two masses is proportional to their masses and inversely proportional to their distances, and that proportionality constant is this g. Likewise, the speed of light in a vacuum has been well understood for a long time, but the ancients thought it was instantaneous, and one can easily forgive them for thinking so because of the high speed of that. The reduced Planck's constant is simply Planck's constant divided by 2 pi, because frequently that 2 pi is part of angular momentum in quantum mechanics. So Planck's constant is basically a way of saying how much energy is in a particular particle. It was needed as a proportionality constant to Planck's law for blackbody radiation. And it is one of the more critical things that is in physics because it also is the proportionality constant for the energy of a photon. It also comes into play when we talk about the energy of quantum states of particles. So Planck's constant will be incredibly important later on. But notice that number is extraordinarily small, 10 to the minus fourth joules seconds, or 6 times 10 to the minus 16th electron volts seconds. So it's kind of a weird unit. It's not electron volts per second or joules per second. It's joules times seconds, which is an odd concept. Well, we'll get more to that later. Boltzmann's constant is also incredibly important as one of the fundamental constants of the cosmos. It is a bridge between heat and statistical mechanics for us to understand energy flow as a product of heat. Now, all of these things, the numbers of these are based off of these SI units of meters and seconds and kilograms and kelvins. And these are all very earthbound things. And they're all units that we're comfortable working with. But they're all based on what humans would measure them to be. And that's not necessarily what everybody in the cosmos would measure them to be. Now, if we wanted to measure them kind of what everyone in the cosmos might measure them to be, we might try to find some fundamental units that aren't so based off of whether or not we orbit the sun and that we're about a meter tall and that we use base 10 as our primary way of thinking, and that we don't think of in terms of seconds and we don't think in terms of kilograms. But let's see if we can figure out these units, maybe called Planck units, which are based off of the idea that you can combine these fundamental constants together to get things that are fundamental to the way of the world in a certain way, or the way of the cosmos. So a Planck length would correspond to, which is 10 to the minus 35th meters. And you could see that it is the square root of the product of the reduced Planck constants times the gravitational constant divided by the speed of light cubed. Now, why would we do this? Well, the Planck length is considered to be a length that where the gravitational influence is roughly balanced by quantum mechanical influences. And so This might be a length upon which we might say, oh, if gravity and quantum mechanics are to be reconciled as competing theories of how the universe works, they work in their own regimes, but they don't necessarily mesh very well. The Planck length might be a good place to look for where they meet. Similarly with the Planck time, which is similar to the Planck length, except you divide by another speed of light squared under the radical. And that's a very short time frame, which is about 5 times 10 to the minus 44th second. So the Planck time might be in a unit of time whereby you can't necessarily tell the difference between a gravitational interaction and a quantum mechanical interaction. That might be one way of thinking about it. The Planck mass is about 10 to the minus 8th kilograms. The Planck energy would be, of course, then the Planck mass times the speed of light squared. And that's an enormous value, about 2 times 10 to the ninth joules, or a huge amount of electron volts, as you can see. The Planck energy is, of course, very large compared to the proton rest mass. So we don't really expect a proton rest mass to be anything related to a Planck mass. Now, the Planck temperature is also interesting, meaning we take Boltzmann's constant and we take the energy and we convert that energy into a temperature. And that gives us a really fascinating statement about saying how heat is transferred on quantum mechanical scales when the density of material is indistinguishable between gravitational influences and quantum mechanical influences. Planck temperature is expected when it would be the temperature expected when something is all compacted down into a Planck length, or a Planck mass is compacted down to a Planck length. Maybe that's a good way of thinking about it. But the Planck temperature is a unique thing that can be devised from these fundamental constants. Mostly what these Planck units allow us to do is they allow us to treat these fundamental constants truly as conversion factors. So if the speed of light is 300 million meters per second, then 1 second equals 300 million meters. Likewise, then we can say for all of our equations in Planck units that c is equal to 1. It's just 1. And that likewise, we can say if we're working in Planck units, then Newton's gravitational constant is equal to 1. And the Boltzmann constant, K, is equal to 1. Now the Planck constant, the reduced Planck constant, is also set equal to 1 in these units, in Planck units. We then say that everything's a length. 1 second equals 300 million meters. 1 kilogram equals 7 times 10 to the minus 28th meters. And 1 Kelvin is equal to about 10 to the minus 67th meters in these units, which is a very weird way of thinking. But now, using the idea that everything's a length and setting all these values equal to 1, we can understand that there's some non-human-centric ways of thinking about units. Now, funny enough, Planck's constant works out to be 10 to the minus 70th meters squared. So it's an area rather than a length, but we can still set it equal to 1 and use it in these length units. All of these things are done such that you can simplify equations. But if you then say, wow, Einstein's great equation, E equals mc squared, now becomes E equals m in these units. That just sounds and looks weird, but it tells us something also, that mass and energy truly are the same thing, and the conversion factor between them is simply this unit conversion between seconds and meters. So we can think of these conversion factors as helping us understand that we can geometrize almost everything in the universe down to a length. And that's helpful in the equations. But for the sake of clarity for the rest of this course, I'm always going to include the C's and G's and H's and Boltzmann constants and so forth. I won't remove them. You will see that in many graduate level textbooks and treatments, but I think that's pretty confusing. So I'm going to let you understand that we can use these as conversion factors, and they're somehow converting things between space and time and mass and heat. And let that be as a kind of a philosophical way of thinking. But it's also extremely useful mathematically and also helps us what would be fundamental in measurement across the universe, irrespective of the nature and source of the observer. With all this in mind, let's go over the briefest possible history of cosmology. Cosmology has been with us since the dawn of human civilization. Earliest peoples, pre-civilization times, must have looked up at the night sky and seen the stars and wondered if they were campfires like their own. And they started to tell stories, and those stories made up constellations, and we made stories about the patterns in the sky. Eventually, when civilizations arose, such as ancient Egypt, the goddess Nut was was the goddess of the sky, and she overarched the earth. Her brother Geb is the earth, but at night her body was said to shimmer with the stars, and during the day the sun god Ra raced across her to traverse from her feet to her head every day, and then repeated it. What the sky was, what she was overarching, how she went through that wasn't important. The explanation was the gods were making sure of that. We've left these gods behind now, and we see how this progresses. These early stories come from 2000 BC, almost 4,000 years ago today. But 1,500, 1,600 years after these ideas were first conjured by the Egyptians, the ancient Greeks, in the form of Aristotle, came up with other ideas about cosmology. Aristotle believed that the Earth was at the center of the cosmos and was unmoving and fixed, and had a real problem with parallax because he said that if there's some parallax, we should see them moving in the sky as you go from one place to another. But he was understanding that the Earth was round and that the Earth was in the center of many celestial spheres upon which the planets rode, and the sky was one of them. Contemporaneously to Aristotle was Aristarchus of Samos at roughly around 300 BC. He developed a heliocentric model 400 years before Ptolemy created his geocentric model. And Aristarchus's model said that the sun was the center of the solar system, and because it seemed to be the largest object. And in fact, he was able to make rough calculations using eclipses to the relative sizes of the sun, moon, and Earth, and found that they were and their relative distances too. So the sun was deemed by him to be very, very large. And so therefore he philosophically put it at the center, not because of any scientific idea, but because fire is nobler than Earth. However, Aristotle's idea won over Aristarchus's ideas because of parallax. If the Earth were moving, then we should see parallax in the stars, which we do not see, which Aristotle and the Greeks couldn't see. But that stuck around for a long time. The demonstration of the size of the Earth came with Eratosthenes, who roughly around 200 BC described a process by which he could measure the shadows of a stick standing straight up at noon at the solstice or particular times of day, or the lack of shadows down the hole of a well. And so the difference between two locations on the Earth, one at the equator and one about 7 degrees below the equator, was enough to give him an estimate for the circumference of the Earth given the distance between these two cities. And that proved that the Earth was round and was a sphere back in 200 BC. Roughly about 150 AD or so, the middle of the 2nd century, Claudius Ptolemaeus created an Earth-centered cosmology where the Earth was at the center of the universe, and every one of the planets in the sky, the wandering stars, the planetas, these wandering stars were each fixed to a celestial sphere that rotated around the Earth, the sun included, the moon included too, and the stars were on their own celestial sphere. This idea, this cosmological idea, lasted for nearly 1,500 years. 1,300 years later, Nicholas Copernicus came up with the idea of a sun-centered cosmology, where the sun was at the center and the earth went around the sun. Now, he didn't do this because of any scientific idea. No, he felt like it was more aesthetically pleasing. In fact, all of the problems that Ptolemy had with his ideas around the center, the earth, the sun-centered universe, where he had to put epicycles upon epicycles and equants and deferents, they were also present in Copernicus's idea, because Copernicus, like Ptolemy, believed that all of the heavens had to be in perfect circles, and these perfect circles were a requirement of the heavens, because they still stuck with Aristotle's idea that the earth was corrupt and the heavens were perfect. So this idea still existed. One of the greatest proponents of Copernicanism was, of course, Galileo Galilei. In 1609, published a paper that predominantly tried to push the Copernican system. He looked through a telescope in 1609 and saw that the sun had sunspots. The moon was not perfect. There were more stars than could be seen with the naked eye, and that Jupiter had its own set of moons or stars that went around it. He called the stars going around Jupiter the Medicean satellites, because he was trying to get money from the family Medici, and it worked. His idea, though, was based on Copernicanism, and that Copernicanism was not really the real thing. Contemporaneously to Galileo was Johannes Kepler. In 1609, he published his ideas about the orbits of planets. He was trying to understand, as he said, the mind of God and how things worked. And so when Tycho Brahe died in 1601, Kepler obtained Tycho's amazing observations of the location of Mars in the sky and determined that planetary orbits were ellipses, which are different than Copernicus saying all planetary orbits are circles. And planetary orbits being ellipses, where the sun is not the center of the ellipse, but one focus of an ellipse, which is different than the sun being the center of all the orbits, such as Copernicus said. And Copernicus also said that the speed of every planet in the orbit is constant, but Kepler found that the speed varies as the planet goes around. And the orbital period of the planet around the sun is related to its average distance through the relationship that he found, which was the orbital period squared is the same as the average distance cubed. Now, the orbital period has to be measured in Earth years, and the average distance has to be measured in astronomical units, or the average distance between the Earth and the sun. Now, he did send this in 1609, sent his copy of his book Astronomia Novia in 1609 to Galileo, who completely dismissed it, thinking that it was really hard to read. And later in his life, Kepler said, yeah, this is too hard to read. I can't even read it. We'll go now forward to the latter part of the 17th century and the early part of the 18th century with Sir Isaac Newton, who showed that the laws of motion of the heavens are exactly the same as those on Earth. He developed his law of inertia, the law of force, the equal and opposite law, and of course his law of gravitation, that showed how Kepler's laws can be derived from first principles. Newton's law of gravitation became an incredibly important element in understanding how things moved. His F equals gmm over r squared equation that showed how forces worked allowed for the understanding of planetary orbits. Now, it's really interesting to think, if you look at Galileo's book on the description of two world orders, he got very close to the concept of an infinitesimal, which Isaac Newton used in his calculus in order to solve the concepts of gravity. However, it took until 1729 when James Bradley finally published his observations of Gamma Draconis, where he was trying to see stellar parallax. He found something else. He found stellar aberration, and that is the thing that showed that the Earth was moving through space. And finally, a proof, in the 1729, over 2,000 years after it was proposed by, a sun-centered idea was proposed by Aristarchus of Samos. Now that Aristotle's ideas had been put to sleep by that observation in 1729, 61 Cygni was observed to have the first measured parallax by Sir William Bessel in 1838. This parallax was approximately a third of an arcsecond, and that's about that's 11,000 times smaller than a degree. And he found that the first star where its distance was known through parallax of about 11 light years or 3.5 parsecs was seen in 1838. Now that Aristotle's parallax had been taken care of with Bessel's observation of 61 Cygni, which is understandable why Aristotle would not have said it. It's such a tiny effect that it is not possible to see with the naked eye. And finally, understanding that the Earth was actually moving and giving Galileo finally some rest in his grave, Foucault's pendulum in 1851 showed that the Earth was rotating because if the Earth is a sphere and rotating, then it's a rotating reference frame. And if it's a rotating reference frame, it'll exert a Coriolis force on a pendulum. And that's what is seen. The pendulum itself precesses due to the Coriolis force. The period of the precession depends upon the latitude at which you are on the Earth. So if you're at the North Pole, it'll be a 24-hour precession. And the closer you get to the equator, the longer and longer and longer that'll be. And that's all due to the fact that we're in a rotating reference frame. In 1917, Albert Einstein developed his theory of general relativity, which allowed for the understanding of the combination of space and time and mass, and showing that space-time and mass interlock and interlink, meaning mass tells space-time how to curve, and space-time curvature tells mass how to move. And that is a fundamental idea inside of general relativity. Contemporaneously to Einstein's work, Vastos Slipher at Lowell Observatory between 1914 and 1922 were measuring he was measuring the radial velocities of bright nearby spiral nebulae or galaxies. And he found that they had a systematic redshift, but he did not think that they were anything cosmological. He was just making good measurements. In 1929, Edwin Hubble was able to get distances to many of the galaxies that Slipher had gotten for redshifts, and he got redshifts of his own for many of the same galaxies. And he found a relationship between the redshift of a galaxy and its distance, and he was using Cepheid variables in order to find those distances. Therefore, finally had an idea that the universe seemed to be expanding. And this was the first observational evidence, and it's been supported time after time after this time. Next, because of the war effort in the Second World War and the work on nuclear bombs, Big Bang nucleosynthesis was something that was researched by many of the same people working on the Manhattan Project. Ralph Alpher in 1948 published a paper that showed that if the universe could be thought of as running backwards in time from Hubble's expansion that was discovered and go to a smaller and smaller state, it would be hotter and hotter and eventually should be hot enough to form elements and do nucleosynthesis. And so that is the birth of the concept of the Big Bang. As a result of Alpher's paper in 1948, it was understood, or at least put into the literature, that there should be a background radiation that exists throughout the cosmos as a result of this cosmic nucleosynthesis, and it should be in the radio frequencies today. It was forgotten for a very long time period, but this prediction was incredibly important. In 1964, Penzias and Wilson discovered the cosmic microwave background that had been predicted by Alpher, Beta, and Gamow in 1948. And they were doing it because they were doing some radio research for Bell Labs in Princeton, New Jersey. And they accidentally discovered it because it was a background hiss they couldn't understand with their radio receiver. The observation of the cosmic microwave background was first put into incredibly strong footing in 1992 by the COBE satellite that was launched by NASA. And it showed that the cosmic microwave background is a perfect black body at a temperature of 2.725 Kelvin. And it was one of the most perfect black bodies ever seen. And I was actually at that conference in 1992 when this was announced. It was an enormous standing ovation with everybody in attendance at the American Astronomical Society. The Hubble Space Telescope was in the sky, and one of its major things that it was going to do was to try to discover the rate of expansion of the universe, and teams led by Perlmutter, Schmidt, and Reese were looking for the expansion rate of the universe, and at the time, people thought that it was going to decelerate. And so people were looking for the deceleration of the universe. And in 1998, the cosmological community and the universe was astonished when it was discovered that the universe was not decelerating, but rather accelerating. And this was the first time we understood that the universe was suffused by dark energy, which took up most of the universe, at least three-quarters. In 2013, on the heels of NASA's Wilkinson Microwave Anisotropy Probe, ESA's Planck mission released its results and determined the age of the universe is 13.799 billion years old. And the accuracy to which they determined the universe's age was better than we know any of the fossils in any museum. It also determined that dark energy made up about 68% of the cosmos, and dark matter composed about 27%, with normal matter making roughly about 5% of all of the universe. With all of this information and the materials that are coming out of the James Webb Space Telescope, we're in a golden age of observational cosmology. Cosmology has left the realm of stories around campfires told by people or religions and has become a precision science that has hypotheses and observations and tests and experiments that can actually determine the nature and age of the cosmos. This entire course will cover all of the aspects of cosmology, from the theoretical side to the observational side, to the observational tests, to general relativity, to all of these things. And we'll look at many of the new results that are happening as a result of the latest observations from the James Webb Space Telescope. I'd like to take a moment here and thank all my Patreon supporters. Without their support, it's really hard to keep going and doing this. But it's just as important for you to subscribe to this channel and like the videos that you see and share them around. There will be a lot more videos because the textbook is long. So I hope you'll stick with me through this fantastic course as we learn cosmology together. See you soon.